So hello, I will be talking about how to do fast parsing of XML and HTML documents in Haskell. So the problem we see here is that of long-term data evolution. So there are formats that need to survive like 20 years, 30 years, and we would like to be able to parse the data for a long time after it has been produced. And frequently, this data is held in complex data structures that need to be extended gradually. And then we also need to be able to transmit this data fast and transmit it between different programs. So we need to have a parser and a printer for each data type. And to address this problem, we have seen development of meta formats, right? Like UTF-8 text that contains anything, protocol buffers, or JSON, JavaScript object notation, or XML in particular. Since XML addresses a lot of these long-term data evolution issues, and there is a lot of existing data like spreadsheets or word processing documents. This data is already in XML. I will discuss how to treat XML in Haskell and do it fast. So the state of the XML ecosystem is that we are able to use generic parsers because we have generic data for meta format. Example is XPath, but it's very slow. So people use the document object model parsers that generate whole data structure in memory and then manipulate it. But then after parsing like 100 meg document, you can find yourself with 5 or 10 gigabyte document object model, which is significantly slowing down all the processing. That's why people like opening of element, attribute, or text, you generate an event that is consumed as a stream. And there are also some parsers that are pretty optimized. There is ASM XML that had a cron for being the fastest 32-bit XML parser. There is Puji XML that is currently holding the cron for being fastest 64-bit parsers, and he does it by cleverly replacing the text of the parsed document with pointers in place, so it doesn't allocate any new memory. And this way, it converts the text input in place into pointer data structure. There are even FPGA accelerators for XML parsing. And for generic data formats, generally such FPGA acceleration doesn't seem to make sense because of the quantity of data that is to be processed, and sometimes the low latencies required. So if we look at the XML document formats, we actually see a format nearly in every industry. So there is electronic document interchange for business documents. There is fixed XML for trading exchanges, financial trading exchanges. There is PDB XML that is protein data banked files for 3D structures of the molecules. There is Microsoft Open XML that is a collection of data formats in XML that hold the spreadsheet information, styling information, and word processing documents. And then this collection of XML documents is usually zipped together to make it smaller and transported as a single file. And this file you can see on your computer as XLSX file. So this Excel file with X at the end, docx, and other similar formats. There is also OpenDoc, and of course, important format, which is SVG, right? Scalable vector graphics that probably a lot of you use for editing vector graphics. So they are all XML documents. That allows the formats to evolve gradually over tens of years, but that also means that the parsing requires more effort. There are also other formats like GNOME configuration files. So if you look overall at like format market from the point of, say, percent of Stack Overflow questions per month, right? You see an interesting trend that most of the questions are asked about few major formats, and most of the data is actually stored or exchanged in these few major meta formats. And here you see that for casual data exchange, for new developments, a lot of people use JSON, mostly because that means easy sharing with the front ends. So the amount of people that are interested in XML data exchange seems to drop, which may be a bit of concern for long-term data evolution, because we are so focused on quick, rapid development that these JSON documents may be difficult to read after 20 years or expand. If you are interested in JSON document parsing in Haskell, you can look at my YouTube talks on JSON autotype, where I try to deliver the schema for existing JSON documents. Luckily, for XML, we already have this schema. We already have kind of data type declarations for most of the formats that I mentioned before. Is just available. There is XML schema, and you can use it to convert it to a data type. And of course, there is CSV data format, ubiquitous for tabular data. That is the easiest to parse. So these three data formats, meta formats, dominate nowadays. Example XML document is here for self-documenting and self-descriptive formatting. You see, first it starts with declaration of XML version and encoding. Then there are elements that need to be closed. So you see the users means in the first line means that the users element is started, and /users at the last line means that users element is ended. So it has this tree structure basically, right? And then inside these elements for structured data interchange, we usually use either subtrees or the text that represents some data types. This is a sample description of the user. And then we would have XML schema that represents what is inside, that enumerates what elements are allowed, what is their type inside them, whether it's flat type or complex type or subtree type, right? How many times the element may occur. So is it like optional, means that it can occur 0 or 1 times. If it's mandatory, it will be at least occurring 1 time, at most 1 time. If it's just a list, then we see the max occurrence number is unbounded. And there are many things you can do with this description. So you can comment it, you can enumerate where you have attributes, where you actually use any XML content from possibly another format. You can also refine the description of the collection. So there are sequences, there are alternative choices. There are also sequences that can occur in any order. And there is also very special part, which is the subtrees that can contain freely intermix text and elements. That's what is used usually in HTML in the content. So you also have a lot of fancy distinctions, like between flat types and tree fragment types, right? There is also a permission to use many character encodings. That makes the problem of parsing XML document relatively hard compared to other formats. So there is already one solution in Haskell space. This is a fast parser that creates a generic DOM file. There are also slower parsers that allow you to read wider spectrum of documents, but we are usually interested here, at least during this talk, in fast parsing of large documents, like spreadsheet ML, which is part of Microsoft Excel files. Then we will talk about how to make it even better, because I told you that few hundred of megs of XML will give you few gigabytes of DOM, document object model. So how to make it faster. And also, since we have XML schema, we would like to import this XML schema as a data type into Haskell, right? And then use it there. And also, there is a problem with speed of parsing XML files. XML files had their adoption hindered seriously because of the slowness of parsing, because this is complex format. And in particular, parser like XPath can take much longer to parse XML file than it takes just to read them into memory from disk, right? So that's an issue, because some people would like to accept XML documents in real time and have millisecond responses. So the first thing we do to be able to parse different string classes is that we have a vectorized string format. What I mean by vectorized, we want to be able to use SMD, SIMD, or anything that speeds up scanning of the document for the next token, right? And in order to do that, we actually don't need to implement a very complex data structure. Vectorized string is basically something that allows us to access character at any index and then find the first occurrence of a character or a subset of characters, and then extract it as a substring and reference it in the code. Right? So drop and null are basically cursor operations, right? So we push the cursor forward and check whether the input has ended. LM index from arrows for vectorized search for the next token. And index and substring allows us to extract the result string and reference it in built data structure. So the pre-existing parser that creates DOM is used like this. So first we import xenodom, then we read the file, we parse it, and then we start filtering all the nodes in the result for one particular that we are interested in. That is inconvenient because we lose all the type information in XML schema, and we just check for the element names. That's quite low level, right? So even though Xeno is fast, the processing of data parsed by Xeno is not so fast and not so convenient. So we want to do it like a type provider. So XML TypeLift is a code generator that generates the data types like this one. For the XML document that I have presented to you in the beginning, there is this users, which is basically a list of Haskell records. And it generates just a parser that takes a byte string and returns this data structure or error message. That's much more convenient because we can immediately start writing business logic code instead of focusing on parsing at all. And this is an example that basically we read the file with bytestring interface that we call the parse method, and we just map over all the names. Just the label of the record is used instead of searching for the elements that are names. Unfortunately, here we have forgive me, but it looks like the presentation is a little bit broken, so I would resize it. So HTML presentations have the merit of being accessible in the browser, but sometimes the formatting is a bit off. Sorry for that. So we see that if you look at the speed of XML TypeLift is actually comparable to Pudgy XML, say, which had held the crown of being the fastest parser, and that is very convenient. And memory use is, of course, higher than Pudgy XML, which does everything in place. So usually it would actually use less memory. But if you look only at the parsing process, we actually, because we do it in place, so most of the temporary intermediate information is garbage collected. We also have not much worse memory use compared. Here we display everything relative to the size of the input, right? So in order to reach that point, we experimented a lot with possible ways of parsing XML documents. So first we parsed with Zeno to document object model. Then we tried to emulate the SACS event parsers, which basically create a event data structure for each token, and these tokens are then parsed. Then we use the offset array, which is basically array where you see the for each fragment of the input the reference to where this fragment starts, and you put it in another array of integers that are basically these offsets. And in this array of integers, you preserve this fixed record structure. So this is keeping records by offsets to be able to cram the parsed data structure better in memory, not to use too much memory for large data sets. And at the same time, preserve the memory safe interface. So you cannot crash. You can just go with offset over the limit, and then you will get warning from Haskell that you are trying to reach over the size of the array. Also, all these offset arrays are packaged within the code that is automatically generated, so the chance of the error occurring there is much smaller than in manual code. So you can freely use this offset array without actually knowing that there are offsets. You just access the Haskell records, which is type safe and memory safe and convenient. The fourth experiment was initially that we tried to inline the string comparisons into separate character comparisons. Parser 6 actually, in this parser we tried to use applicative interface, and finally we used both offset arrays and inline string comparisons. And it turned out that after all these experiments, we used the best ideas to implement this code generator that was very successful. So the final result was that we used offset arrays and inline string comparisons and applicative combinators to make the best parser. So the final code looks like this. So it's quite understandable what happens here. You can actually read it, although it's not encouraged. I would rather use the code generator as a black box. It is available as a GitLab repository, so you can use it as a type provider for your own documents. And if anybody wants to implement like a new parsing of the another string encoding or another XML feature in the code generator, you are welcome. It's open source. Any questions?
Thank you for the presentation. If you could raise your hand for the questions, then I can hand the microphone over. Okay, we have here this question.
Hi, great talk. Thank you so much. I was wondering, how much does laziness like affect the generated? So if I just want to access a user's name, right? Does all the rest of the XML file still get parsed? Like I just want to access the first user's name in the list. Let's do that. Yeah.
So in this case, the entire file will be parsed because most of the use cases we had would be requiring that at least the whole data structure is available, right?
Okay.
And we only put the results, basically put the pointers into offset array. We don't generate the record data structures for the name, for example. Yeah, so this part of generating the records, Haskell records, is done lazily. We just pre-process the whole data structure to create these offsets that allow for efficient access of any part of the XML document or any data that is inside, and then you can create the records and browse them lazily.
Cool. Thank you.
Hi, someone, which is what happens if there's a syntax error somewhere in the input? Are we assuming that doesn't happen? Or if it's a malformed input, are you able to parse the well-formed parts and make those available? Or how does that work?
So basically, we check for XML well-formedness first, right? So whenever there is a syntax error, we actually return this error message eagerly, right? So that the interface takes the byte string and returns either error message or the data structure that contains the offset arrays.
Okay, so if there's a syntax error anywhere, then none of the data is available.
Yes, that's true.
Right.
We consider developing the HTML-friendly version that basically allows you to skip certain parts and thus parse incorrect file format, but it's not ready yet.
Okay, thank you.
There are some more questions here. So if XML is just a very verbose description of a tree, why choose XML over some other textual representation? Maybe. Yeah.
That is a good point. I think it is complex data format, but has the advantage of allowing for addition of subtrees or additional attributes or additional annotations at any point of the tree. And a lot of effort has been put into designing it this way. As far as I'm aware, other tree-like data formats are less amenable to upgrade. So basically, if you use just S expressions, right, then whatever change you make into the format, this subtree will be difficult to parse. If you use XML and you add element in the middle, then previously valid parser can just skip this element and go on, right? That's the main difference. So you are able to make like backwards compatible.
Okay, and next question, how does a user of TypeLift know what names and types will be generated by TypeLift?
So they are generated from the XML schema, but they have to be modified because they have to adhere to Haskell naming conventions. So they will be similar to the names seen in the XML schema.
Do you happen to know of such generative approaches in other languages? Another nice question.
Yes, so I am aware that there are type providers for F#.
Mm-hmm.
And I would generally recommend in every language to try to use this generative approach. If it's not available, please consider building it if you need to parse a lot of document formats.
And the last one, if you are referencing the input text in resulting structures, then doesn't it hold onto large chunks of memory, even if I need only a small part?
So the technique we use to read the input is basically memory mapping of read-only data. So the virtual memory systems should allow us to just discard these fragments that are not needed anymore. Mm-hmm. But yes, we hold on to the reference for efficient reasons.